Thanks, Scott. All right, so what Scott was trying to say is that I'll probably be back up here in November, so you'll get very, very tired of me. So those of you that don't know me, I'm Rishee. I'm a colleague in civil and environmental engineering. And my work is in the area of urban informatics, and we'll talk about that. But what I thought I would do first was tell you where my current mind space is. And that is here. I just got back from sabbatical. This was the view from my back patio. And I wanted to start here to sort of set the tone of how I'm sort of approaching this. I think often, and I do this too, we start these talks with doom and gloom and all the problems that the world is facing. But I still have the halo effect from sabbatical. So I'm thinking about the amazing things that society can offer us and the positive aspects. And that's actually what excites me about being part of our school, is the possibility of solutions. And part of that is really thinking about how we drive the top line of sustainability. And what I mean by that is how we maximize things instead of minimizing them. You know, I think we're often focused about minimizing environmental impact, minimizing negative impacts, but how can we actually maximize things? And so that's where my current mind space is. The other thing is I'm pretty sure I was looking at this photo when I enthusiastically responded to Scott, happy to do the faculty forum at the start of the fall quarter. Yeah. Life's looking a little bit different now, but it's still looking up. So for me, thinking about this in terms of top-line sustainability, it really is focused on thinking about how we maximize building and energy systems' positive impacts on human well-being. So what those two systems can do to make our lives better. So with that, I'll jump into, so my lab is called the Urban Informatics Lab, and if you want to just think about it, it's really thinking about how we model and develop solutions between three systems: people, buildings, and energy systems. And we do this on three different scales. So the first scale is what we call intra-building dynamics. So think about what's happening in this building, how people move in this space, how we heat and cool this space and light this space, this sort of things. The second is zooming a little bit out to the community scale, how clusters of buildings perform, how communities actually evolve. And finally is all the way at the urban scale, how you think about policy for decarbonization for an entire building stock, say for the city of San Francisco or any other major region or city. So what I thought I'd do is give you a flavor for some of the work we do in each of these sort of areas and go from there. So we'll start with intra-building dynamics. So first, can anybody tell me what movie this is from? You get, yeah, bonus points. That works even in with faculty colleagues. I thought, yes. So this is the famous movie Office Space, one of my favorite. This is me, that's Arun. I'm just joking. But I think what the point is that our offices don't really look like this anymore, right? The cubicle farms are not really as norm. They've evolved to something like this, but we can argue, have they gotten better or worse? You know, there's challenges that. And then we had COVID, in which it taught us a few things. It taught us the main thing that we took away was that some in-person interaction is necessary to break down silos. I think that's the motivation for getting us all together on a Friday afternoon. I'm guessing Scott and Arun and, and Vanessa who organized this, but it helps break down silos. So, this is part of the ideas of what's going on. But the reality was that our offices were broken, or our buildings were kind of broken even before COVID. We've probably all been in a situation like this where we're in a building that is too cold or too hot, and we're spending way too much energy and not maximizing that human benefit. We're not feeling comfortable. So that's what motivates some of the work that we do in this. And you can think about this is that we think about this on two different sides of the coin. First, we think about occupants. Occupants occupy a certain space at a certain given time. But they're also in an office space because they are interacting with colleagues either on the same team or they're having lunch with a friend or doing something like that. So they have those social and organizational networks that are important. And then building systems also operate on space and time. This is our air conditioning systems, our lighting systems. They should be on or off at certain spaces and certain times. So what the goal of this work is how you sort of reconcile these dimensions for those of them and align them. So we did a study with an office in San Francisco, and I'll call this just privacy-aware occupant state inference, where we can start to tell when people are working at their desk and how they're working. Happy to go into the privacy awareness of this, but the short answer is we did not use video cameras because that was just not going to happen for many, many different reasons. We used a very cheap sort of plug load sensor that could infer some of these things as to whether folks are there. So I'll point out, this is 4:45 p.m. in this office. Red means folks are there working. Yellow means they're in an in-between state, which we characterize. And then green means they've gone for, or they're not away. So as you see the day evolves, you start to see that folks are leaving in that part of the building, but are still here. And there's a possibility for realignment. Maybe if you move folks around, you can shut down the systems in one part of the building and only heat and cool the other part and use lighting systems in there. Sounds pretty easy and cool, hard to motivate people to do it. So of course, we did a study to see what would happen if we did this in a 150-person plus office. Great, we saved 5% of energy. It's a pretty low-cost solution of just moving people around. Took this to some colleagues who work for a company that rhymes with Oogle. I'm not going to give you any names, but they told me, hey, Rishee, this is cool, but you know what? We probably are not going to implement it, because this is how we think about things. Energy is $1. Space is $10, maybe $20, depending where you're on the Bay Area. And people are $100. So if we're not incorporating the people dimension in this, then it's a hard sell. It's a hard sell to move people around and do this. So that got us thinking, and credit goes to one of my awesome PhD students, Andrew Santa, who's now a faculty member at EPFL in Switzerland, who said, hey, let's start thinking about this a little differently. And when he took some classes over in the business school, it's a long bike ride away, but not that far, with Amir Goldberg, who's an organizational scientist and thinks about how teams come together and do work. We started to think about this to say, hey, there's some opportunities for social interaction. If we start to understand when people are available to interact with their colleagues, sometimes you want to be heads down working, sometimes you're not even there. How do we maximize this so there's some collaboration? This work was all done pre-COVID, and so it's actually, it sort of died down for a little while, but now that folks and companies are bringing people back in hybrid, it's becoming interesting again. So this is a time series of one individual from 7 a.m. to 7 p.m. Once they're in red, they're kind of in the office, and then here's how we sort of code it. We say yellow is a good time when they're actually okay with interacting. Maybe they're doing some light email work. They're doing a few things here and there. And we can see another person, and we can start to identify potential opportunities for this social interaction. So this could make a more collaborative space. We can also look at this over time of when do these interactions occur, when do these opportunities occur. This is pre-COVID, so you see a pretty stable base between Monday and Friday or through the week. But in hybrid work, it's even different. And so as you start to gain this knowledge, our future vision in this is to really think about how we design energy efficient and collaborative spaces. Because then we can really hit that top 100 mark. So we can sort of piggyback onto sustainability by saying, how do we use energy in the most effective manner to maximize that human output? And so that's where this work is going. So we'll now move to the community scale. And with that, I invite you to board an emissions-free flight to Mumbai. Virtual, of course, and instantaneous, right? So, but of course, emissions-free. So this work is really centered around informal settlements, and the reality is that 1 in 8 of people on this planet live in informal settlements, colloquially known as slums. The challenge here is there's a push for redevelopment. Many of them are in prime real estate. So they're going to get redeveloped, and once they're redeveloped, there's 50+ years of lock-in effects. And there's huge implications for people's lives, like energy burden and thermal comfort. So that's what kind of motivated us for some of this work. But the challenge here from a research and standpoint is that data is really hard to get. This is me back in my younger days when I had more hair, out in Dharvi in Mumbai, actually doing on-site interviews with a colleague from Cambridge, installing sensors. But it really was hard to even get 5 dwellings instrumented like we needed to actually do any modeling. So it actually became a very interesting research question. How do you actually model data-sparse environments? How do you start to model these interactions when you don't have a lot of data? So kind of the opposite of the office where we could put in lots of sensing or these sort of things, or even other communities here closer to home. So it turns out what you do is you do a little data and a lot of building physics. So the way we started thinking about this is, hey, we can collect some data on some characteristics. We can build an archetype of what that looks like and calibrate that model. Then we can sort of define some morphologies and some key design parameters based on local literature of design practices. And then we can start to do some sensitivity analysis to explore the solution space. And while we can't get exact numbers of what's going on, we can start to identify what are the big low-hanging fruit for some challenges, in particular regarding heat stress. And then we can evaluate what are the situations and what we can do. So we did this across many different informal settlements across the world. And we modeled 3 types of short-term retrofits: increased fan ventilation, cool roofs, and overhang shading. Then we also modeled some redevelopment scenarios, and I'll share a little bit of the results. So the first thing to jump out is, well, I guess the first thing to see in this is that these are 4 cities we modeled: Bangalore, Jakarta, Mombasa, Mumbai. Blue means we're reducing the number of hours of heat stress. Red means we're actually increasing it. So the first thing to see is there's some low-hanging fruit. By implementing cool roofs, we can actually significantly reduce the heat stress events that's occurring in these communities. So actually working on with a colleague from the School of Medicine that we'll see gets funded through this Climate Adaptation Accelerator call on thinking about this and implementing this in Makassar, Indonesia, to actually do some measurements on the impact of human health. The second thing, though, I wanted to point out is that when you do redevelopment, these are 2 simple scenarios we modeled. You actually see a big difference between the 2. So my opinion is that redevelopment will happen and should happen eventually. And so what this points out is we have to carefully think about that, because we could actually make things worse by not doing it carefully when we're talking about heat and thermal comfort. So things to think about. Okay. The future vision here is actually thinking about natural cooling and comfort, but we have changing environmental conditions. A big part of my work is advocating for natural cooling and thinking about this, but that's based on a flawed assumption that the air is clean outside and there's challenges. We've all been way too familiar with this, but in addition to that, this is my DIY natural cooling with a HEPA filter I built during COVID when my kiddo was a year old and we were sweating in our apartment. But it's starting to evolve as to what we want to do, and now the idea is how do we think about it with changing environmental conditions. All right, I'll take a deep breath, and then let's zoom out. We'll fly back here, back to the Bay Area, and come back to San Francisco to talk a little bit about the urban scale dynamics. So this is the famous or infamous Salesforce Tower. In current way of how we think about modeling this, if you're a modeler, you think about the Salesforce Tower and you model it as if it's in the middle of a green field. But the reality is that we know that the buildings around it actually impact its energy usage and its energy dynamics. B, C, D, and E are buildings around it. They have impacts related to heat transfer, shading, and the urban heat island around it. And so we started to develop a series of tools for different stakeholders that could be developed at the urban scale. The first, and I will say that I can't take credit for the acronyms. This one goes to the students who decided to continue it on. I thought the first paper came out as DEWS, which is Data-Driven Urban Energy, and then they and I was like, we should come up with new names, and they came up with on themselves to continue the acronyms as we went on. So the first one is for designers and owners. It's really trying to ask the question, what is the energy impact of design changes or retrofits given this urban context? And it sort of takes the power of data-driven models, machine learning, but combines it with the physical models that we do. The second one is for policymakers. If you're looking at an entire city and you try to ask which are the ones I should be targeting if I'm trying to reach a particular decarbonization goal, who do I give a passive incentive to? Who do I go and send an energy auditor to and incentivize them to use something like that, a little more sophisticated? And finally, if you're thinking about this from an urban planning perspective, what are the impacts other urban systems have on the energy usage? Don't have time to go through all of them, so I thought I'd walk you through just the DEWS model and our thinking behind it and some key results. So what we do here is we create a baseline energy simulation. We combine it with machine learning, and then we can do some nifty things. The key thing to think about is why combine these two things? Well, the physics-based models are really, really hard to scale up. You need detailed information about what's in the building, what kind of materials are in it. And on the flip side, the machine learning models can't actually predict anything, especially if you change the underlying physical dimensions. So if you go and you say, I'm going to retrofit in a particular building, now the ML model sort of falls apart because it's never observed this type of data. So in summary, I think I'm running out of time. I see Vanessa looking at me. I will highlight that when we implemented this in Sacramento, in Sacramento's downtown area, by using this kind of model, we could actually reach their decarbonization goals by retrofitting 50% less number of buildings, if you can sort of exploit the aspects of the urban context. And this opens up pathways for large-scale system synergies on renewable energy and transportation. And that's really where the future vision is on this, is trying to think about the challenges we have around affordable housing, land use, and energy sustainability, and how they all come together. So with that, I will say thank you for spending some of your Friday afternoon, and hand it back over to Scott. Oh, I guess there's time for questions.